Right, so now let's look at the formal definition of what a commitment is. So we define non-interactive commitments. What is the syntax? So the syntax is that it has these two phases. So it has the commit phase. So here, let B be the bit that needs to be committed. The sender generates a state, psi sub B RC on registers R and C, and sends register C to the receiver. The states psi sub B, B01, can be generated using a polytime algorithm from the all zero states. So that's the commit phase. So this needs the state generation needs to be efficient, and this is the most general thing that they're going to look at, because we already argued that we want it to be pure by assumption. Okay, and then reveal is the following: that the sender sends B together with register R to the receiver, and the receiver is going to measure whether the state was psi sub B or not. And if it happens to be psi sub B, the receiver outputs little b, which is the opening. Otherwise, the receiver outputs bot, which is bot whatever. So rejects the opening. Okay, and note that this measurement here, right, that is being done can also be done efficiently, because you can prepare the state efficiently. So you know the unitary that needs to be applied to prepare the state, and then you can run it to check. You can do the inverse of that unitary and check that you get all zeros, because that's how we generated psi sub B to begin with. Okay, and what is the correctness condition? The correctness condition is that, so perfect correctness is that when the honest sender commits to little b in 0, 1, the probability that the receiver opens, the honest receiver opens to little b is also 1. Sorry, did I say also? Sorry, no. If the sender commits to B, which could be 0, 1, the probability that the honest receiver opens to B is 1. Okay. Yeah, when they're both honest. Okay, good. Now, definition 3.3 is going to tell us what the notion of hiding is, and this is related to the sum binding. Oh, sorry. That's correctness. Okay, yeah. So I think binding will appear later. So hiding is the following: that consider the following game, experiment B with parameter B, which is 0, 1, between a challenger and a challenger C and a QPT adversary A. And this is the game, right? So you have the challenger generates the state, sends register C to Alice, and B prime is the output of the experiment. And we say that non-interactive quantum commitment scheme is computationally hiding if for any PPT adversary A, there is a negligible function such that when you run the experiment with B0 or you run it with B1, the output is, the probability that you get 1 is negligibly close. And the output here is this, right, the bit which is output by the adversary. So basically saying that irrespective of whether the commitment was for B0 or B1, little b equals 0 or little b equals 1, the adversary A cannot distinguish these two cases. So that's hiding, and that's computational because A is a QPT adversary. Right? Now, for binding, we have the following. So so we want statistical binding, and here the notion is of sum binding. So consider the following game, right? So there's the challenger, and here's the adversary. So now the adversary is the sender, right? So it's preparing some arbitrary state, ERC, and it's going to send register C to the challenger, and that's the commitment. And then the opening, say the adversary A wants to open to little b in 0, 1, then we assume without, the most general thing we can think of is that A applies some unitary U, which is U0 or U1, depending on whether he wants to open to 0, 1, on registers E and I. E is the environment in a sense, and register I is sent to the challenger. And the challenger is going to measure as before using psi b, and psi b was, remember, defined using the honest construction, right? It's going to make this measurement, and if it gets the first outcome, the output is B, otherwise bot. Okay, now, so suppose P little b is the probability that A makes C open B, right? So this is what we were saying. So it's the probability that the malicious sender can make, the receiver open to B. So this is not hard to see, right? Just from the way we define psi and U here, right? That you apply psi and then you apply U to sway towards 0 or 1, depending on what little b is, and you trace out the environment. And then the probability that the receiver is going to output little b is just the probability that the outcome is psi b, which is exactly this probability. Now we say that the commitment scheme is statistical sum binding if for any bounded a, just a second to make sure the microphone is. Oh, it is working. Okay, sorry. Just wanted to check that the microphone. Okay. So we say that the commitment is a statistically sum binding if for any unbounded a there exists a negligible function such that p0 plus p1 is at most 1 plus negligible. Okay, I excluded the negligible because it was just an outline of what we wanted. Okay. So that is the definition. Hopefully that's clear. Now let's move on to the construction. So the construction says the following. So we use the notation state gen to denote the procedure that outputs, on input k, outputs the state phi sub k. And we use b to denote the bit that has to be committed. Okay, so these are the two notations we use. And state gen corresponds to a single copy secure PRSG. So the commitment phase is as follows. So this we already essentially saw. So psi sub b is going to be defined, using x set k in the R register. There's no E register for us, and the C register is going to just be the pseudorandom state, and you apply or don't apply the quantum one-time pad depending on whether B is 0. Okay, so we're going to skip that. And in the reveal phase, the sender just sends register R and the bit B to the receiver. The receiver measures the state with, these two things. And if the result is psi B, the receiver outputs B. Otherwise, the receiver outputs bot. Okay, and such measurement can be done efficiently, like I was saying earlier. So we were going to. So suppose VB is the unitary that had to be applied on 0 to obtain psi sub B. And the measurement is basically that you apply V dagger B, and then you measure the computational basis and check whether the output is all zeros. Right. Okay. And now it is clear that this construction satisfies perfect correctness, right? That is because simply by definition, essentially, right? Because this is how you constructed psi B, and you will get exactly psi B with probability 1. There's no. So yeah, the overlaps are perfect. And now for okay, so let's move on. So this part is simple. Now we are going to make a small remark before we actually do the analysis, and the remark is the following. So here, the reveal phase also had quantum communication, right? So we had quantum communication for the commitment phase, but the reveal phase also had quantum communication. It turns out that this part one can make completely classical. And the way one does this is as follows. So basically, one applies a one-time pad also on register R, okay, and then you send both registers R and C to the receiver. Okay, so earlier we were only sending C, now you send both R and C, but before you send R, you also apply this extra Pauli pad. And when you have to reveal the, if in the reveal phase, when you want to give an opening to B, you send the bit B together with the one-time pad X set on the register R. So, okay, so C was whatever it was. Okay, I'm not talking about that. I'm just saying that assume that you have a scheme that, uses psi sub B RC as the, the general commitment scheme. Then we're going to apply the one-time pad only on register R and construct a new scheme. So instead of sending just register C, you send both R and C. And when you want to open, you open by sending the bit B and the classical bits or the classical strings X and Z corresponding to the Pauli pad applied on register R. Okay. And the receiver can basically then undo the one-time pad, and then you're essentially in the same position as the original and run the original verification algorithm because you're in the same position as the original protocol. Now, hiding is clear, right? Because before the reveal phase, the register R is essentially maximally mixed, right? Because you used fresh keys for the one-time pad that was applied on register R. So no information is revealed. And for binding, suppose there is an attack in the new scheme, then essentially one can run the same attack in the original scheme, right? Whatever you were trying to do, you can just do it on your side. And so basically you have that the new scheme is no more secure than the old scheme. So every attack in the new scheme can also be carried out in the old scheme, and so you're as secure as the original scheme. You don't lose anything. Okay. So that was the first remark about making the communication classical in the reveal phase. The second remark is that one can extend the argument even in the case where the PRG is, the pseudorandom state generator, PRSG. Oh, shoot, I've been writing it wrong. Okay. So let me write it down for my side. Page 11, PR, pseudorandom state generator, and not PRGs. Okay, sorry. So I have to make that correction. Okay, and then these PR pseudorandom state generators also output some ancilla, and then this ancilla one can essentially account for by absorbing it in the R register, right? And everything else essentially goes through unchanged. All right. So now we can finally, so we have the construction, we have the definitions, and now we can argue that the security proofs actually go through. So for computational hiding, we have the following theorem. So we show that the construction satisfies computational hiding. The way it works is as follows. So we start by defining hybrid zero, which is the same as the original experiment. Okay, so the hybrid zero, so the zeroth hybrid is as follows. The challenger gets input B to commit. It generates the state psi sub B exactly as we saw in the original scheme, sends register C, and the adversary has to output B prime, right? So this was exactly the hiding property that we wanted. For hybrid one, what we're going to do is when B is 0, we're going to sample a uniform, a hard random state. And when B is 1, we're going to send whatever was sent in the first hybrid. Yes, we'll send psi 1. And okay, the rest is the same. So we first show that these two hybrids are the same. Our probability of outputting 1 in both hybrids is the same for each B0 and B1. So it's evident that for B equals 1, the hybrids are exactly identical. So the probability of getting 1 is going to be 1, right? So let me actually copy this hybrid on the side so I don't have to keep scrolling. So here. Oh, what happened? Did I stop the screen? What? Okay. Yeah, I hope it was recording the screen share. Otherwise, it would be very long. All right. So we have the. Sorry, this. Okay, this is good. Right. So we have the construction right here. And now what we were trying to argue was that when you run hybrid 0, actually let's put hybrid 0. Okay. So it's evident that when B is 1, right, hybrid 1 and hybrid 0 are exactly the same, right? Because you're sending psi 1. So this part is trivial. Now what we're going to do is we're going to look at what happens when the bit B is 0. So contradiction suppose that the difference is actually non-enumerable. So what we're going to do is we're going to create an adversary A prime that's going to break the security of the pseudorandom state generator. So the challenger for the pseudorandom state generator is the following. So it's given the input B double prime, and if B double prime is 0, it's going to output a pseudorandom state. And if B double prime is 1, it'll output a hard random state of n bits, mq bits. Okay, and it will send this state phi, depending on whether, yeah. So there should be a little b if you want, or b double prime, but it doesn't matter. So, okay, so the state phi is sent, and now A prime is going to basically forward whatever state it got to A, where A was the adversary playing whichever, it was playing the hybrid games, right? So here it's this A. And this adversary is going to output little b, because that's the syntax, right? It expects a register and then it produces some output. And then A prime is going to basically output the same output. Maybe I could have put a prime here, but it doesn't matter because there's no conflict with B. Okay, now the main thing is that when B double prime is 0, so A's view is essentially the same as what it would see in hybrid 0, right? Because when B double prime is 0, the state being sent is a pseudo-random state, right? And indeed, since little b is set to 0, right? This is what we're trying to distinguish. So hybrid 1, little b 0. So you get hybrid 0, little b 0, you get a pseudo-random state, right? Because only register C is sent. And there's no b is 0, so this thing doesn't apply. The one-time part doesn't do anything, right? So you get C, register C. So that part is good. So indeed it sees hybrid 0. And then when B double prime is 1, A is going to see hybrid 1 of 0, right? So hybrid 1 of 0 is what? An actual hard random state. So if there is any advantage that A has when it plays against hybrid 0 or hybrid 1, then A prime is going to have essentially the same advantage against the PRSG security. And so therefore, if A breaks the security, so if A satisfies this, then A prime breaks the security of PRSG. Okay, so that's good. Now let's define the next hybrid, because we're still not done. So the next hybrid does the following. It's going to output a hard random state irrespective of little b. Okay. Okay, and in this case, we want to show that hybrid 2 and hybrid 1 are the same. So again, when hybrid 1 is given input 0, it's going to produce a hard random state, which is exactly what hybrid 2 does on input 0. So these two are going to be the same. And what remains to be shown is that what happens when B is 1, right, in these two cases. Now, again, for contradiction, suppose that on B equals 1, they have non-negligible probability. Then one can construct, there's the probability that they output 1, the difference is non-negligible. So then, so if there's such an adversary, then one can construct an adversary A prime that's going to break the security of the pseudo-random state generator. And the way it works is as follows. So C prime is going to, again, as before, send a hard random state or a pseudo-random state. And A prime is going to, so here's the difference, right, from the previous case. The difference is that this state psi1 now has P, this state psi1 has the permutation, not the permutation, sorry, the one-time pad acting on phi sub k. So A prime is going to make sure that the format matches by sampling X and Z itself and applying X and Z to the state phi and sending it. Okay, and then whatever answer it gets, it forwards it as its own answer. So whatever answer A prime gets from A, it forwards, A prime forwards that as its own answer. Okay, so now the note is that when B double prime is 0, right? So when you're getting a pseudo-random state, then it's exactly the same as hybrid 1 on input 1. So hybrid 1 on input 1, you get psi1, and psi1 is exactly a pseudo-random state with a random permutation. So that's exactly what A sees. And then when B double prime is 1, then the state that is sent by the challenger is a hard random state. And we know that applying a one-time pad on a hard random state continues to keep the distribution be exactly the same as a hard random state. And so this is the same as output 1 of the hybrid, or the second hybrid, right? Which is actually always just a hard random state. Okay, good. So this allows us to conclude that the outputs of hybrid 2 and hybrid 1 are also going to be the same for all efficient adversaries. And finally, this is completely obvious because so the claim is that the hybrid 2, or whether you give it 0 or 1, the outputs are going to be exactly the same because, well, the challenger doesn't change its action depending on B. It always sends a hard random state. So combining all these three observations, we basically conclude that the hybrid 0 on input 0, outputting 1 is the same as the hybrid, as the same hybrid on input 1, outputting 1. Okay? So basically means that you cannot, that the adversary cannot learn which message was sent with non-negligible probability.